want to talk a little bit about Fourier series, which many of you will see as you go on in math or physics or engineering. And I want to give some applications, one of which is totally standard and the other of which is answering the following max-min question. Take a curve in the plane that has a given length, arc length. Okay, so assume it's a C1 curve. Among all C1 closed curves, C1 curves of a given length, which one gives you maximum area? So this is a max-min problem. We've been doing max-min problems for 3 weeks. Thought it was a good way to end the class.
Circle.
So we did discuss if you took triangles or quadrilaterals of a given length, maybe we didn't do quadrilaterals, but triangles of a given length, what gives you the maximum area?
And
Equilateral. So you want to guess the answer to this?
it's a circle.
It's a circle. An equilateral curve. It's a circle. And this is actually a big theorem in differential geometry called the isoparametric inequality. So those of you who eventually take Math 4250 may see this in that course, but it will not be with this proof. So I'm actually going to use Fourier stuff as an application to give you a proof of this, which I think is very cool. Okay, so today we're talking about the space of continuous functions. For the moment, I'll say on the interval minus pi to pi. That's our vector space. And our inner product is defined by integrating the product of the functions. So this is very similar to what we were doing with sums on Friday. There's a 1 over pi for reasons you'll see in a minute. And this is analogous to doing the summation AK BK when we were doing the series. Is it, if you put a constant in, does it pull out? Sure. If you take a sum of f's and take the inner product of g, is that the sum of the inner products? Sure, because integrals of a sum are sum of integrals. Symmetric? Sure. Interesting one. If I do f inner product f, is it always greater than or equal to 0?
Yes. Yes. No. Yes.
Yeah, because you're going to have the square.
You're integrating the square of a real function, so it's non-negative. Is it 0?
Only when f is equal to 0.
Only when f is 0, because of continuity. Without continuity, you wouldn't know that. Okay, so it's an inner product. Let me say that if you wanted to think about complex functions, which is actually easier, but I don't want to do that today because I can only do so much. We'll talk some about this stuff at the end of 3510. Fear not. For complex valued functions, you would use the inner product. It's usually with a 2 pi, and it's f times the conjugate of the complex number g of t. So you have complex conjugates where you take a plus bi and you turn it into a minus bi, and that means that when you put f inner product f, you're integrating f times f conjugate, which is magnitude squared of the complex number, and that is positive again. But I'm not going to mess with this. Okay, why did I put the 1 over pi there? Well, can you give me an obvious orthogonal set of vectors in this vector space? Think of some functions. So one natural way to think about this is think about periodic functions on all of R, and then sine and cosine come to mind. So we could look at cosine of kt, and we could look at sine of kt, where k is a natural number. You're missing an obvious function.
The zero function.
That's a somewhat less obvious function.
Equals x. F equals x. T equals t.
Now, what's the easiest sort of functions in general?
Linear.
Easier. Constants.
So zero.
But I wanted non-zero constants.
Oh.
I think
should
we'll
ask for
see
none.
it-
So what would happen if I took f and g both to be 1?
You'd get 1.
I would integrate 1 from minus pi to pi, I would get
2 pi.
over pi. So
pi's.
what the length squared of 1 would be 2. If I wanted
Not obvious.
my orthogonal set to be orthonormal,
It would have to be.
remember orthonormal set means orthogonal to one another and unit length. So I would have to do what with my 1, since it had length squared 2,
You have to take this
divided by square root of 2. So I would take 1 over square root of 2 to be my constant function. And the reason for the 1 over pi is that if you integrate cosine squared or sine squared, from negative pi to pi, I'll let you do this, you get pi. I'm not going to take the time to do the integrals. So that's why the 1 over pi is here, because that means that cosine of t will be a unit length vector, and sine t will be a unit length vector. And you can check that putting any integer there doesn't change this. So in fact, it's true with k's here. Just make the substitution and check. So these are unit vectors. Once I come over here, what's amazing, and again, it's easier to see with complex stuff, which I'm skipping, amazing observation, is that they are actually orthogonal to one another. If you take the integral of cosine kt times cosine lt, or you take the integral of cosine kt times sine of lt, or you take the integral of sine of kt times sine of lt, you always get 0 when k and l are different. So if you draw yourself a cosine and a sine of different, or actually, sorry, this is true, this one is true for all k and l, and these are true when k and l are different. You can sort of convince yourself, take yourself a cosine, for example, there's a cosine, and now do a sine times it. Well, then from what you did on homework, you know the answer is 0. If you put a sine wave in here, and you multiply them, you get an odd function. So from what you were thinking about on homework, integrating an odd function from minus pi to pi is always 0. So this one being always 0 is obvious. What isn't so obvious is a cosine times another cosine. Oops. So if I took a cosine of 2t, I would have to oscillate twice as fast here.
You'd have to oscillate through them. It would be up at the top, right where the middle is? No.
multiply those, you're going to get canceling areas. So the integral is 0. If you really want to check this, boring homework, there are formulas, for example, for things like this. Again, this is easier to do if you know some complex number stuff, but there is a formula that looks something like, and I'll never remember it. Oh, good, I wrote down the one that's not in my notes. So what shows up with products of cosines? Well, the formula, addition formula for cosine does, right? Cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. Does that ring a bell?
Yeah.
So I ought to be able to solve for this by combining a cosine of alpha minus beta with a cosine of alpha plus beta. Then these will cancel. So if I add these two together, I'll get twice. So what should I do? I should take 1/2 cosine of k minus L t plus cosine of k plus L t. So integrating this product, you would integrate these. And as long as k doesn't equal L, this is going to integrate to 0. So you can check that yourselves, but I'm not. It all works. So what's the point? The point is you can take a subspace of your continuous functions that is spanned by the first capital N of these orthonormal basis vectors. You could take the constants. You could take cosine t, sine t, cosine 2t, sine 2t, up to cosine nt, sine nt. And you could ask yourself, given any continuous function, given any vector in this space, what's its projection on Vn? Given any f, denote by script f sub n of f. If you don't like script, do something else. The projection of f onto v sub n. So this is going to be what's called the finite Fourier series for the function f. I'm just building f. I'm asking what periodic function built out of the first n frequencies is closest to my continuous function f in the exact sense we've been doing here. Here's your space, which I can't draw quite with all its dimensions. And you've got these various finite dimensional subspaces that are spanned by these first n frequencies. And you're taking a general vector and you're projecting it, just as we did with vectors in R3 or Rn, you're projecting it to get what I'm calling capital F sub n of f, which is supposed to be the point in this subspace closest to f. You would think that as you made n bigger and bigger, what should happen?
It spans all of C, so and
You end up
f of
making
n
everything
of
zero.
f equals f.
You should get closer and closer because these, if you make n bigger, the subspaces are all nested. You're taking a thin subspace inside a fatter subspace inside yet a fatter subspace, and so your projections get closer and closer to your f as you take n bigger. So as n gets bigger, the magnitude of the error vector should go to 0. That's not obvious, that's a theorem. And so, in some sense, we expect that the limit of these projections, as you take bigger and bigger capital N's, should more or less be your function f. Now, how do we compute the projection on a subspace? So I'm tying this back into what we've been doing. How do you compute, if you have a subspace of Rn, how do you compute the projection of a vector into that subspace?
You can do it with, since you have multivariable basis, I'll use it with just some vectors.
So from our earlier work, you would compute this projection by taking the sum.
From I equals 1. The sum of
Yeah.
from I equals 1 to what, n?
Well, so I've got sort of,
N
I
plus
have
Equals
2n plus 1
2n
vectors
plus
here,
yeah.
right? So the sum of the projections of f onto these, so maybe we need some notation here. Oh, well, I don't know. Projection onto sum over the 2n plus 1 orthonormal basis vectors. EI, let's say. So you would take the sum of the projections onto those orthonormal basis vectors. So let's write down what you would do. How do you do a projection onto a unit vector? You just take inner product with the unit vector times the unit vector and add those up, right?
You're right.
This is projection d.
And I keep doing this until I get to the frequency n things, right? This is frequency 1, frequency 2, frequency 3, up until I get to frequency capital N. Oh no! Okay. And so what you have is a term that I'll call A0. That's this term. And then you have a bunch of cosine terms. Right? This is the AK. This is A1 times the first cosine, and so on. And then you have EK. And if you've looked at web work, this is what they're asking you for, these A's and B's. And what are these coefficients? Well, they're just these inner products of your function with the appropriate unit vectors. So, where AK is 1 over pi integral f of t cosine kt. That's that dot product, right? That's the inner product. When you do f inner product cosine kt, you're integrating f times cosine divided by k. So that's the kth Fourier coefficient. Bk is the same thing with sine. And what's A0?
It's the first term.
Well, I integrate minus pi to pi, leave a little room here. F of t times 1 over root 2 and then multiply by 1 over root 2. So instead of taking 1 over pi, what do I have?
1
1 over 2 pi times the. So this is just the average value of f. Remember average values from your BC calculus course or from Calc 2? You have a function on an interval, and you want its average value. You take the total area and divide by the length of the interval. We'll see this a lot next semester for multivariable as well. We'll do lots of average values. Okay, so I want to do an example for you. So I want to take a function, the simplest function that you already suggested other than constants, and I want to compute what its Fourier coefficients are. So I'm going to take the function f of t equals t. So it looks like this. Square both sides? T is having a power attack.
Precautions.
Just precautions.
All right.
All right.
So, symmetry ideas. If you have an odd function, what do you think happens to these coefficients here?
They get bigger.
If you have an odd function, would you expect to have even terms showing up?
No.
You would expect only odd terms.
Right.
Just like with tailored polynomials, if you have an odd function, only odd degree terms show up. So what you would expect is that if you integrate an odd function times cosine, you would integrate to 0. Well, that's obvious, because odd times even is odd. So if you integrate t, cosine kt from minus pi to pi, it's going to be 0. So a0, the average value is 0, and all the ak's are 0 by symmetry principles. Or you can do the integral, if you, again, if you don't trust me, do the integral. I'm about to show you how to do it. How do we do bk? Well, it's 1 over pi integral t sine kt. How do I do this? How do I integrate t times sine t? Parts. Remember how to do parts?
Yes.
I remember the principle behind it.
U is t, dv is sine kt dt. So du is dt, and v is
Like minus cosine
Minus cos kt over k.
over k.
minus 1 over k cosine kt
kt.
plus constant. But I'll take the constant to be 0. So what do I get? Integration by parts says the integral of u dv is uv evaluated at the endpoints, of course, minus the integral of v du. So what do I get when I do this? Sorry to keep you awake. Cosine of a multiple of pi, but then you have the same thing minus pi.
Oh, 0.
Those are the same, right? If you're at k pi, you're at the same point on the unit circle as k minus pi. K times minus pi. So these cancel. Oh, wait a minute. I'm confused.
Yeah.
Cosine values are correct, but they're not the same quantity.
Wait a minute, I'm confused.
It's just the cosine
So I-
gets
The cosines are the
And
same,
it's
but I have to worry about what's happening here. So
No, 'cause
it's canceling too. You have to take minus pi over k, cosine of k pi, minus
Right.
negative pi. You following me?
Why'd you triple minus? You should only double minus. You triple minus.
No, it's triple minus.
Is it triple?
No, it's right.
Negative, negative, negative?
Isn't it just because you're gonna have
Technical term.
a zero, the same thing multiplied by 0?
No, we're okay. We're okay.
Technical term.
We're okay. This is
Negative,
not
negative,
canceling, in fact. This is correct. Let's be patient here. And then what do I get? Plus, and this is all times a 1 over pi, sorry. Bookkeeping is hard.
I know.
And now I have to integrate cosine kt from minus pi to pi. What's that? That's going to be 0. You're integrating cosine over a period, you get 0. So this is 0. So what am I left with? I'm left with
Pull out the negative pi of
the
k.
pi's cancel. I'm left with negative 1 over, so let's factor out a 1 over k. The pi's cancel. I've got negative cosine k pi
Plus pi over k is
minus
No, pi.
cosine of negative k pi. Now I told you these guys are the same.
Yeah.
So I'm going to have 2 over k. What is cosine of k pi? It's minus 1 to the where did that come from?
Is that the Taylor series?
Right? If you're an
Uh,
if you're an even multiple of pi, you're there. So you have minus 1 to an even power, which is plus 1. Why did I put a k plus 1? Because of the extra minus sign. And if you're at an odd multiple, then cosine k pi is negative 1. So you've got negative 1 to the k. That gives you plus 1 when k is even, and minus 1 when k is odd. And then you have an extra plus 1 from these. So this is, believe it or not, this is b sub k.
I choose
That's
to not.
those are the Fourier coefficients for that function. Now here comes some fun. You guys okay?
Are we relating this back to that circle thing?
Hmm?
That circle thing we started out with at the beginning.
Oh no, I'm getting there. I'm not there yet. I'm not there yet. I'm not there yet. I have another application first. Okay. Now, if you have an orthonormal basis and you compute the components of f with respect to that basis, what do you expect to happen? You expect that you take the components with respect to your basis vectors, add them up, and then you take the length squared. Right? If you take whatever vector and you write the vector x in terms of coefficients, then of course if you have this with respect to an orthonormal basis, you get that the sum of the squares of your coefficients is the length squared of your vector. Well, the same thing's going to work here. So this is called Parseval's formula. Nothing to do with Wagner as far as I know. That the length of f squared, which is 1 over pi times the integral of f squared is the sum of all these Fourier coefficients squared. Now, for reasons of the 1 over root 2's, that's why that 2 is there. So you add up all the a's squared and all the b squareds and your constant term, and that gives you the square of the length of f. That's just because you have an orthonormal basis and you compute length from the coefficients. So let's apply this for this example. Here are all my a's are 0. So I'm supposed to have the integral of t squared. That, right? F is t. So I'm computing f dot f. So I integrate f times f. What do I get? What's the integral of t squared?
T cubed over 3.
T cubed over 3. So when you plug that in, at minus pi and pi, you'll get
Pi cubed over 3 minus
2 pi cubed
2
over 3.
pi squared over 3.
Oh, yeah, because then, yeah.
Did I do that right?
Yeah.
Okay. On the other hand, what do I get when I take the sum of all the squares of the b's? So what do I get? 2 squared is
4.
minus 1 to any power squared.
1. What about the k? Okay. Oh.
Pi squared over 6.
So this gives you a proof of the very famous formula that the sum of the squares of the reciprocals is pi squared over 6. So that's your first application for the day. If you take complex variables, complex analysis, sometimes you'll see other ways of doing it. Okay, so that's a really cool application of part of the notion of Fourier coefficients. And as promised, now I'm going to answer Taylor's question. So you would not think, if you were a normal mortal being, that Fourier coefficients of functions on an interval have anything remotely to do with the question I asked at the beginning. But there's a neat fact that you can prove that was first observed by a mathematician named Theodore. It says, suppose f is C1, and I'm going to switch, instead of doing minus pi to pi, I'm going to shift from 0 to 2 pi. Just for reasons you'll see. Suppose the integral is 0, and you integrate from 0 to 2 pi. Then, the integral from 0 to 2 pi of f squared is less than or equal to the integral of f prime squared. So this seems like a really good calc exercise. And equality holds if and only if f of t is some multiple of cosine plus some multiple of sine. is going on?
I suppose my answer is
Well, here's a proof, in quote marks. It's a fact that when f is C1, the Fourier series of its derivative is, guess what?
C0.
What did you do with Taylor series? You had a Taylor series for a function. What would you do to get the Taylor series on its derivative?
Oh, and derivative of Taylor.
You take the derivative of the Taylor. Same thing works with Fourier with reasonable situations. So if you started off with f being something like this, what would f prime be? Well, you would differentiate, and you would get k's pulling out by the chain rule. Parseval it. This is given by summing the Fourier coefficient squared. So first of all, this tells you that A naught is 0. The average value is 0. And now Parseval tells you that integrating f squared is pi times the sum of the squares of all the Fourier coefficients. That's this. And Parseval tells you that doing f prime squared, you get pi times the sum of the squares of these coefficients. Well, looky here. What's the coefficient of cosine kt? It's k. So you see it? This is pi sum k squared times what I've got in the first sum. Well, of course these are bigger than or equal to these.
Yeah.
Because you've got the same terms, but here you're multiplying by positive integers, bigger than 1, except when these terms are all bigger except when k is 1. When k is 1, this matches. So how can these be equal? The only way they can be equal is for all of these guys to be 0 when k is bigger than 1. You can't have any terms showing up when k is 2 or bigger because these would beat out those terms.
Oh.
Isn't that nifty? So this is a very unexpected use of Fourier to prove this inequality. Now, you might not see why this inequality is relevant, but I'm going to show you why it's relevant. Any questions on this? All right, so here's the isoparametric inequality. If C is a closed curve with length L and enclosing area A, then L squared is bigger than or equal to 4 pi A. The square of the length is at least 4 pi times the area. And what happens if you try a circle? You get pi r squared,
It'll be
and you get 2 pi r quantity squared, and they're equal. So there's still lots of research going on in these days, even in the modern era, generalizing this kind of question to higher dimensions with various conditions and lacks of conditions. The proof is due to Hurwitz from over a century ago. This is not the proof I usually give when I teach differential geometry, but it's a really cool proof. It's sneaky. So here's an assumption I'm going to make, just to make our life easier. Assumption, let's say L is 2 pi, just to make our life easier. And parameterize C by arc length. Remember arc length? So that the distance you've moved along the curve is the integral of the speed so you're always moving with speed 1. That's what our parameterization means. So how would we get L? Well, you would get L.
You already said that L was 2 pi.
Right, I did. But, so I want to say L, which is going to be 2 pi, but it's the integral of, this is the sneaky part, right? We did this, so I'm just going to use T, because I've been using T's today. You integrate the speed, right? That's what we did a few months ago. Take the integral of speed, and that tells you how far you've gone. But because the speed is 1, this is the sneaky part.
Then it's 2 pi.
Because I'm integrating 1, I can integrate 1 squared. I would never have thought of this, but this guy Hurwitz thought of this. So what are you integrating? You're integrating x dx dt squared plus dy dt squared. I'm still confused about something.
If he's confused, we're doomed.
Uh-oh, I may have to fix this tomorrow. Yeah, so I'm a little confused at the moment. Okay, oh.
Is it going to go back to Fourier?
No, I want to use this, but I'm confused about where to get, this is 4 pi.
A. No. It's 2 pi. Doesn't
Ah.
be 4 pi squared. Squared pi. Problem solved.
Okay, I think it's okay. So the end of the argument, this is the sneaky part, which so we're going to do this. I'm going to take L squared minus 4 pi A, and we're going to say, how do I get A? Well, I'm going to get A by thinking about Calc 2 and saying, as you parameterize your curve, you're going to integrate y dx dt. So as you move along your curve, you're used to saying the integral of y dx gives you area. But I'm parameterizing it by t, so I'm going to put in my chain rule here and say I'm going to integrate with respect to t, but notice that if I move counterclockwise around the curve, I'm doing y up here as I'm going backwards, or minus y down here as I'm going forwards, and so there's actually a minus sign. So this is actually giving you the area. We'll talk about this next semester when we do Green's theorem. So we'll spend lots of time on this. But now the trick is this. Take this, so I'm running out of time, so I'm going to just get to the punchline. Okay, so I'm going to subtract a multiple of the area. Since I had a 2 pi already, I need a 2. Yeah, so I need a 2, and then I'm going to have y dx dt. All right, so let me just get to the punchline here, and then we'll quit. This is really cool. So you complete the square. You say dx dt plus y squared gives me dx dt squared plus 2y dx dt plus y squared. So I have to do a dy dt squared minus y squared. Well, this is integrating something positive, and what did we have in our lemma? The integral of y squared is less than the integral of dy dt squared. That's this. Assuming that you've chosen your coordinates so that the average value of y is 0, you can just shift your coordinates so that the average value of y is 0. Then this integral is positive,
That one's positive.
and this integral is positive by the Vertinger thing. So
it's positive.
this difference is greater or equal to 0, and it's 0 only when y is a cosine t plus b sine t, which means you're going opposite. Okay. So I finessed a little bit of the arithmetic on how this turned into this. So that's what you have to stop and think about a little bit. But this is the ultimate sort of continuous version of a max-min problem that leads to all sorts of open questions in mathematics. I just thought it'd be cool to end the course with a max-min problem that used Fourier, so there you go.
Where does the negative 2y dy dt go?
Yeah, well that was, there's a factor of, there's a 2 pi that's pulled out, and then you have a minus 2 times this integral. So writing this as 2 pi times 2 pi minus 2a.
Oh, no? Still don't see it. I thought I saw it for a second.
And this integral is 2 pi. This integral is the arc length, which is 2 pi.
Right,
And then this is minus 2a.
Right.
So that becomes plus twice.
right. But then over here, when you did the complete the square thing,
Yeah.
I don't see how that distributes back out to what that is.
Sure. The cross term. This times 2.
Yeah,
Yes, but what about the other one?
then you have.
What other one?
You completed the square.
I completed the square, so the extra y squared I subtracted out.
Yeah.
But don't you?
What?
When you square this, you get the x to t squared plus 2 y
Right.
dx dt.
Got it. Yeah, no, I don't have a problem with that.
Plus y squared.
But then you,
Then this term is here,
right.
and I subtracted the extra y squared.
But what
I
about
got
the,
for this.
the cross term?
There's no cross term, it's not big squared.
This is squared minus
Oh,
squared.
it's not big squared. Got it. Okay.
Square both sides. All right, guys, sorry we ran over a bit.